Yesterday we have seen the integral mode of a PID controller. We have seen that it is function of old error, other drawbacks with integral mode. Because of integral mode, it go on integrating. Suppose go on integrating means it may integrate beyond 100%. It may integrate beyond 100%. Are you able to understand what I am saying? M of t equal to Mi of t. Mi of t equal to Mi of t means what? Integral mode. That is Kc by Ti integral of E of t dt. The Mi of t may increase beyond 100%. Suppose the error is not zero, not yet become zero, because the system may have lag or dead time. If the system has, let us assume that the system has dead time means dead time means what? Even though if you give enough input, the output will come after some time. Are you able to understand? Let us assume that the system has a dead time of 20 seconds. Dead time of 20 seconds. If you give correct input now, when the correct output will come? After 20 seconds. During that time, the integrator will go on integrate the error. That's why what will happen? The output of the controller will go beyond the required value. That is one way. Sometimes a lag also will affect. Lag means what? The output has a delay. Transportation lag. Yesterday we have seen as the order increases, there will be a transportation lag. Because of that also, the integrator will integrate beyond 100%. So integrator do not know that control valve can open only up to 100%. Control valve can close only up to 0%. But the controller is numerical. It will integrate beyond 100% as well as it will integrate, if the error is negative, it will integrate beyond negative value, zero value also. That's why the controller value may become 125%. But can control valve can open 125%? No, it's not possible. Similarly, the controller output may become minus 50% because of negative error exists for long time. The error persists for long time. The controller output may becomes negative. Similarly, it may go beyond 100%. That is called integral windup. That is called integral windup. Integral windup problem. Integral windup problem. The integral windup problem may happen. If integral windup problem happen means, suppose the controller output M of t is 125, let us assume now. But even if you give 125 output, what is the current? 4 to 20 milliamps only. Even for 125, it will be 20 milliamps only. Even if it is 110, it will be 20 milliamps only. 115, 20 milliamps only. That's why valve will open only 100%. Even if you give beyond 20 milliamps, valve will open only 100% only. But now, because of this full open, now error becomes negative. That's why it starts decreasing from 125. It starts decreasing from 125. It takes a long time to reach 100. If it decreases below 100, then only the valve starts closing. Then only the valve starts closing. That problem is called integral windup. To avoid integrating beyond 125, there will be a anti-reset windup technique can be used. Anti-reset windup. The problem is called windup problem. To remove that windup problem, we can use anti-reset windup technique can be used. It should not integrate because it is an integrator, analog integrator. It do not know, it goes beyond 100. It goes beyond 100. To avoid that, we can use anti-reset windup technique. For that, let us first consider the expression for M of t. M of t equal to Kc multiplied by E of t plus Kc by Ti integral of E of t dt. Let us use only PI controller. It has wind up problem. How to remove that wind up problem? For that, this M of t can be written as in derivative in Laplace transform. In Laplace domain, it can be written as Kc E of s plus Kc by Ti E of s upon s. I am writing this assuming zero initial conditions. I am writing in Laplace domain. But this also can be written as M of s equal to Kc E of s plus M I of s. It can also be written as M I of s. What is M I of s? It is integral output. Integral mode output alone can be called as M I of s. M I of s is this part. This part is called M I of s. M I of s, where M I of s equal to where M I of s equal to Kc by Ti E of s upon s. This s, how it came? Because of integrator. Now, from this we can find Kc E of s. What is Kc E of s? Kc E of s equal to Ti s plus M I of s. Let it be equation 2. Let it be equation 1. Substitute 2 in 1. We will get M of s equal to Kc E of s equal to what? Ti s M I of s plus M I of s. Or we can write M of s upon M I of s upon M of s equal to 1 by Ti s plus 1. I got a transfer function. Output is Mi of s. What is M of s? M of s is the controller output. M of s is the controller output. If you take Laplace inverse, you will get M of t. M of t is the total controller output. M of t is the total controller output. Here, this is set point. This is set point. Here I am using a PI controller. This is G of s. G of s. This is the feedback. This controller output may go beyond 0%. It should, the controller output, analytical output may go beyond 100%, but the valve will open only 0 to 100%. So now the problem here is it may go beyond 100%. That's why we are going to design an anti-reset wind-up technique. Here, the controller output is called M of s. M of s. From this M of s, I want to find Mi of s. Mi of s. Mi of s is integral mode output. Mi of s is integral mode output. So from M of s, I can find Mi of s. For that, I am having a transfer function. You can find the electronic circuit for this transfer function. If you give M of s as input, it will give Mi of s. So I am having a electronic circuit that is 1 by Tis. What is Ti? Integral time. I am finding a transfer function electronic circuit for this. I am giving M of s as input. What is the output? Mi of s. Mi of s. Mi of s. Which is go beyond 100%. Mi of s made the controller output goes beyond 100%. So what I can do is I am taking this circuit alone. So if you have this circuit, you can produce Mi of s. If you subtract Mi of s, whenever it reaches 100%, it will not go beyond 100%. Are you able to follow? This is the controller output. This is M of s gives controller output. Whenever it goes beyond 100%, I am putting a switch here. The valve stem is there. The valve stem, whenever it goes beyond 100%, I can put a switch. This is the valve stem. This is the valve stem. In that, whenever it reaches go beyond 100%, I can put a switch here. Switch here. In the valve stem, I can put one contact. It will close this. That's why I can get a closed circuit to activate this circuit. This can be used to activate this circuit so that it will produce Mi of S that can be subtracted here. So here I can put one summing block. From there I can subtract this Mi of S so that it never goes beyond 100%. Never goes beyond 100%. Whenever it reaches 100%, the switch will close. That will generate this that will activate this TAS plus 1 so that this will generate Mi of S that is available here, that will be subtracted from controller output so that it never goes beyond 100%. Similarly, here also you can put one switch. Here also you can put one switch. Whenever it comes here, it will contact with that switch here. Here you are putting in the bottom also, you are putting one switch. This is also connected here. This is also connected here so that when it comes to 0, it will activate this circuit. This switch, this will activate it. The circuit will be activated whenever it reaches 100 or 0%. That time the integral mode output will be generated by this circuit that will be subtracted from the total output. Inside Mi of S is generated, outside Mi of S is subtracted. That's why it never goes beyond 100%. It never goes beyond 100%. This is called anti-reset windup technique. So if you use integral mode, there will be a problem called integral windup problem. To remove that, to solve that problem, we are having a circuit then generate Mi of S. Whenever the controller output reaches 100% or 0%, this circuit will be activated and the Mi of S will be subtracted from the controller output. That time only. Therefore, it never goes beyond 100%. Therefore, there won't be any integral windup problem. But this is for analog circuit. Nowadays, it is digital circuit. How in digital circuit we can implement the anti-reset windup technique means whenever the control output becomes 100, we have to stop integration because we are writing program. That's why we can check if M of t equal to 100, then we can stop. The integrator part can be written here, integral of E of t dt. For that, in digital circuit, it will be sum of E of k. It can be stopped whenever it reaches 100%. It will stop. Therefore, if not equal to 100%, this integral mode will be there. Similarly, if M of t is not less than 0, then only we have to do this integration of E of k. That way we can do in digital controllers, but in analog controllers, we have to have this block to generate Mi of S and it will be subtracted from the total controller output. This is called anti-reset windup technique.